All right, we're going to start section 4.2, which is called Rolle's Theorem and the Mean Value Theorem. Rolle's theorem is actually just a special case of the mean value theorem, so really you could just call this section the mean value theorem. We'll look at that shortly here. But all right, I'm going to start with Rolle's theorem, which says, let f be a continuous function on a closed interval ab, differentiable on the open interval ab, and f of a equal f of b. If we have these three conditions satisfied, then there exists a number which we'll call c in the open interval ab so that f prime of c is equal to 0. Okay, now in other words, if we don't have a horizontal line, Rolle's theorem will give us a guarantee that we will have an extreme value in the interior of a closed interval. All right, let's take a look at a proof of this here. So I've drawn a picture that I'll refer to, and I'll focus mainly on the local max case here. But all right, so proof. Let's let f of a and f of b be the same number, which we'll call k, okay, for some function f. So here's a, here's b, and f of a and f of b are located at the same height. Now, case 1, if f of x is equal to k, like if I draw a horizontal line here, then the derivative is always going to be 0, right? The slope of the graph is 0 since the slope of a horizontal line is 0. So that's not really an interesting case, okay, since f prime of x would be equal to 0 for all x, okay? So here's case 2. Suppose that f of x is greater than k. Like suppose that somewhere between a and b, you have some x value that is going to be producing a y value that is bigger than k. All right? By the extreme value theorem, what did the extreme value theorem say again? It said that if f is continuous on the closed interval ab, then f has both an absolute maximum and absolute minimum on that interval. Okay, so by the extreme value theorem, f has an absolute max. Okay, since I know that f is continuous on a closed interval, I'm guaranteed both an absolute max and an absolute min. All right, we'll just focus on the max case, like I said here in case 2. Since this absolute max does not occur at an endpoint, it is also a local max, right? Local extrema cannot occur at endpoints. Let's let the local max be at the number c. By Fermat's theorem, f prime of c is equal to 0. Okay, so what did Fermat's theorem say again? It said that if f has a local max or a local min at c, and f prime of c exists, then f prime of c is 0. Okay, well, we have a local max at c, and we know that f prime of c exists since f is differentiable on the open interval ab. So I can take a derivative anywhere between a and b. F prime of c exists, therefore f prime of c has to be 0. Okay, so in my picture here, suppose that c is located, somewhere between a and b, and you have a y value that is some number bigger than k. Well, the slope of the graph at that spot has to be 0. Okay, you're producing a local max somewhere between a and b, so somewhere between a and b, you're going to have the slope of the tangent line being 0. Now, case 3 is saying a similar deal as in case 2, but in the situation where you have a minimum value. So if f of x is less than k for some x in the interval ab, make a similar argument as in case 2, but involving minimums. Okay, so in that situation, you're going to have some number that is going to be producing a y value less than k. You'll use the extreme value theorem to conclude that you have both an absolute max and an absolute min in this interval, you're going to have an absolute min, okay, although you'll have both. The absolute min does not occur at an endpoint, so it's also a local min. By Fermat's theorem, f prime of c is equal to 0. You'll let the local min be at, whatever number c happens to be. F prime of c is equal to 0. Okay, so again, the main idea with Rolle's theorem is that it gives us a guarantee that we will have an extreme value on the interior of a closed interval. Okay, so somewhere between A and B, you're going to have a local max or a local min, okay, by Rolle's theorem, if these three conditions are satisfied. Okay, now there's going to be a couple of problems in the homework where you'll be using Rolle's theorem, and before you start the problem, they'll want you to verify the conditions for Rolle's theorem. Okay, when you see that, they're asking you to just check off that these three conditions are satisfied. If any one of these three conditions are not satisfied, the conclusion of Rolle's theorem won't happen. Okay, or at least it's not a guarantee. All right, so that's what they're looking for. Check that the function is continuous on the closed interval AB, it is differentiable on the open interval AB, and that f of A and f of B are the same number. Okay, those are the three conditions. Now, Rolle's theorem can be helpful in solving equations. Now, here's an example. Show that the function f of x equals x cubed plus 5x minus 2 has exactly one real root. Okay, we did some things with roots back in chapter 2 when we were talking about continuity and the intermediate value theorem. The intermediate value theorem is useful in solving equations in that you can be able to show that there is a real root between two values. Okay, so I'm going to, and of course what I mean by a root is it's a number that's going to return 0. Or if I were to solve the equation x cubed plus 5x minus 2 equals 0, there would be 3 answers, but one of them is going to be a real number. And I want to show that, now I don't care what that number is, I just want to show that out of the 3 answers, exactly one of them will be a real number. The other 2 would be imaginary numbers. Okay, now we're going to first show that f has a real root by the intermediate value theorem. Just be able to show that one exists. Okay. Then we're going to play kind of a what-if game. Okay, what if f has 2 real roots? We're going to see what the problem is with that then. Okay, now in this problem here, I'm going to have us show that the function has exactly one real root, and we're going to start off by using the interval 0 to 1. The reason why I've selected that interval is because, well, number one, f is a polynomial, and polynomials are continuous everywhere. So certainly f would be continuous on the closed interval 0 to 1, right? It's continuous everywhere. But the reason why I've selected this interval is because if I plug 0 into f, I get -2, and if I plug 1 into f, I get 4. Now, the intermediate value theorem says that if you have a function that is continuous on some closed interval, AB, we'll call it, then there exists a number, which we were calling C, such that f of C is equal to 0. Okay, so in this case, by the intermediate value theorem, f has a root between these two numbers, 0 and 1, where f of A equals 0 for some A value. Okay, so in other words, because one of the output values was negative and the other was positive, at some point you're going to have to cross the x-axis, right? At some point there's going to be a number that would return 0. Okay? Now, A would be a root of f. Now, what if we have another real root? which we'll call b. Okay, what if like there's another number b, and it can be anywhere on the number line, okay? But another number b exists where f of b is equal to 0. Okay, we'll see what the problem is with that then. So f of a is 0, f of b is 0, therefore they're equal. Now, f is a polynomial, and polynomials are continuous everywhere, right? So f would be continuous on some closed interval ab, and it would be differentiable on the open interval ab. Polynomials are differentiable everywhere, okay? So now the three conditions for Rolle's theorem have been satisfied, right? I've described a continuous function on a closed interval, a differentiable function on an open interval, and f of a and f of b are the same. Well, Rolle's theorem says that there exists a number c in the open interval ab so that f prime of c is equal to 0. All right, so that's where I'm headed next. So by Rolle's theorem, there exists a number c in the open interval ab so that f prime of c is equal to 0. But there's a problem with that, because f prime of x is 3x squared plus 5. 3x squared plus 5 will never be 0, no matter what x is. Right? If you square a number, you'll never have a negative. If you multiply by 3 and then add 5, you'll still never have a negative, but then you'll never have 0. Okay? And thus, f prime of x can never be 0, so this gives us a contradiction. In other words, f of b never existed to begin with. Okay? Because if b was another real root, then we would have f prime of c equaling 0 for some c value, and we don't get that here. Therefore, f cannot have two real roots. It only has one real root, which would be the number a. Okay, now in a problem like this, what we've shown here would be handy, because if I were to solve the equation x cubed plus 5x minus 2 equals 0, which I'm not going to do, but that would be a difficult equation to solve. I have a degree 3 polynomial, so I know that there's 3 answers by the fundamental theorem of algebra. I have no idea what these 3 numbers look like, other than one of them is going to be a real number. Okay? And that real number exists between 0 and 1. The other 2 numbers are going to be imaginary numbers. Okay? Now, to begin a problem like that, I would have to use guessing and checking. That would be my only option. And of course, guessing and checking can be a time-consuming, brutal thing, because I have no idea what this number is. You know, it's some number between 0 and 1 that would be a solution to this equation here. But at least that allows me to get started with the problem. Okay? And I would know, kind of have an idea of what the answers would look like. Okay? There's exactly one real root, and the other 2 roots would be imaginary numbers. Okay, we'll stop right there.